In engineering, a system is simply a collection of interacting elements connected by strict physical cause and effect relationships. The objective of a control system is to force an output variable to behave in a specific, prescribed manner by manipulating the input variables. Engineers map these physical relationships using standard block diagrams. In this structure, the arrows represent signals, or variables, moving in and out of the component blocks. The most basic configuration is an open-loop control system. In an open-loop architecture, the output has absolutely no effect on the control action. A classic toaster operates on an open loop. You set the timer dial as your input, and it runs blindly. If the bread is frozen, it stays pale. If the slice is thin, it burns. A domestic clothes dryer suffers from the exact same limitation. The duration depends strictly on the timer setting. The machine never measures the actual moisture of the clothes. Because open-loop systems are entirely blind to their own results, they rely entirely on perfect conditions to achieve the desired output. The alternative is the closed-loop control system, an architecture designed to maintain a strict relationship between the desired input and the actual output. Unlike the toaster, a home thermostat does not run blindly. It constantly monitors the current temperature. If the room is too cold, the heater engages. The system continuously measures the actual output against your exact target. This process relies on measuring the error, the mathematical difference between what you want and what you actually have, and taking immediate corrective action to reduce that gap. This closed-loop diagram illustrates the mechanism. The controlled output is fed back and compared directly with the reference input. We can map this to riding a motorcycle. The desired speed is the input, and the actual speed is the output. The rider acts as the controller, processing the error and adjusting the throttle to correct it. In automated systems, we replace the human rider with mechanical or electrical devices. To function correctly, they require strict mathematical programming. Feedback loops allow systems to adapt to their environment automatically. However, engineering those automated corrections requires calculating complex interacting math underneath those simple diagram blocks. To understand how engineers build these systems, we have to look inside the process blocks and examine the internal math. Physical system dynamics, like a motor's speed reacting to voltage or a motorcycle accelerating down a highway, are modeled using differential equations. This equation shows a standard time-domain differential model, representing how a single physical component changes over time. Calculating raw derivatives and integrals works perfectly well for one isolated component. But when you link multiple components together in a continuous feedback loop, the math compounds. Algebraically combining standard calculus equations inside a closed loop creates an incredibly dense web of math, making rapid engineering design practically impossible. To design practical control systems, engineers need a way to completely bypass solving these equations directly in the time domain. They require a mathematical bridge, a tool that translates complex calculus into a format they can easily manipulate. The primary tool control engineers use to solve this bottleneck is the Laplace transform. This graphic illustrates its function as a translation tool, moving mathematical functions from the time domain, f of t, into the s domain, f of s. The formal definition relies on an integral from 0 to infinity, demonstrating its rigorous calculus roots. In practice, engineers rarely compute this complex integral by hand during standard system design. Instead, they rely on standardized tables of established transform pairs to translate terms instantly. By shifting equations from the time domain into the S domain, engineers alter the operational rules of the math, setting the stage for massive simplification. The most crucial feature of the Laplace transform for control systems is the derivative property. Looking at this rule, we see what happens to a first derivative. The term dx over dt translates into the variable s multiplied by x of s. Here, the translation does its heavy lifting. Complex differentiation is completely replaced by simple algebraic multiplication. We see this using a basic differential equation with a zero initial condition. Applying the Laplace transform translates each term into the s domain. With calculus gone, we use basic algebra to factor out x of s. Isolating the variable yields the final algebraic solution. Solving for the system's behavior no longer requires integration. It only requires moving terms around, like middle school algebra. The S domain successfully flattens complex physics into flat algebra, making it possible to link system components together mathematically. The formal engineering term for these isolated S-domain equations is the transfer function, denoted as g of s. This equation defines the transfer function strictly as the system's output, y of s, divided by its input, u of s. These transfer functions are the literal mathematical contents of the black boxes we drew in the block diagrams at the very beginning. Because every process is now expressed as simple algebra, entire blocks connected in a series can be combined just by multiplying their transfer functions together. The Laplace transform is the structural glue that allows engineers to accurately map and manipulate complex control architectures on paper. We can ground all of these concepts in one final physical example, driving a car down a highway. The driver's manipulation of the steering wheel maps to the control input variable, u of t. The mechanical physics of the car itself, its weight, tire grip, and steering ratio, are captured perfectly by the mathematical transfer function, g of s. Looking at this complete closed-loop block diagram, we introduce one final element. This downward arrow represents disturbance, or NFT, unpredictable environmental forces like crosswinds that you cannot control but must react to. The car's actual physical position on the road is the final output, y of t, which is constantly fed back to the driver's eyes, closing the loop. By translating physical dynamics into the algebraic S domain, engineers can build feedback loops that calculate and reject wild real-world disturbances, ensuring the system safely reaches its target.